Okay, we're going to look at some general ideas in mathematical modeling and talk about how we use physical principles to develop differential equations. So first thing we're going to do is look at just mathematical modeling itself and some basic ideas. In particular, we're going to look at vocabulary about what does it mean to be proportional and inverse proportional. So the idea is we're going to be looking at mathematical modeling. I cannot spell mathematical, apparently. Basic idea is you're going to start with some physical principle. Right? And once you have that physical principle, you then try to translate those words into mathematical equations. And we'll talk about how we do some of that as we go here. But you don't just stop there. Once you do this, you try to do some kind of analysis and look at how do you use this information to try to understand the behavior. The way it's stated here, it sounds like you go from the principle to the model and then the analysis. It's not quite that simple because you use the analysis to help you try to understand the implications of the physical principle. You always want to come back to this. But you oftentimes go back and forth here and use your intuition to inform how you're going to do the analysis. At the same time, you ask questions about the model itself and ask, are you using everything? And so you go back and forth. And that's going to help go back and give you some insights into what principles are important. So this is an iterative process, and it's not just a linear thing where you go around looking at one thing leading to the other. It's oftentimes a confused mess. All right, so how do we go from here to here? We're going to focus on this idea of going from the physical principle to the mathematical model. But keep in mind, in practice, it's not a simple thing where you just go in one direction. So the first idea is this idea of proportionality. If I say that A is proportional to B, what does that mean? That means there's some number, we'll call it K, and what's special about K is that A is K times B. So the general idea here is if you double B, you double A. Right? If you cut B by a third, you cut A by a third. Okay? If you're given a statement and you're saying one thing is proportional to another, that you should use that to get this expression. Okay, so let's look at an example. So in the example, what do we have? So we have this statement. The time it takes to travel across Athens is proportional to the number of stoplights you encounter. So what do we have? From this statement, you would be expected to recognize a number of things. First thing is, one variable is the time it takes to travel across Athens. Okay. The other thing is you have another variable here, and that's the number of stoplights. So from this statement, you should recognize there's two variables, travel time and number of stoplights. Notice no units are used here, so you would be expected to decide what units. So for example, maybe minutes. In this case, the number of stoplights, that is the units. And then finally, this says that those two things are proportional. So there's some number, I don't necessarily know what it is, but I can give it a name. We'll call it K. And the time for travel is related to the number of stop sign or stoplights by that expression. So given the original statement, you should recognize that relationship. Okay. Another example. So in this example, we have the shear force required to break a cylinder is proportional to the cross-sectional area of the cylinder. So what are the variables? One variable is the shear force required to break the cylinder. So let's just call that SF. So that's some shear force. We'll just assume that's in newtons. The other variable is the cross-sectional area of the cylinder. So we'll just say that CA. Okay, and we are given that those two things are proportional to one another. And that means that the shear force is related to the cross-sectional area by the shear force is equal to K times that cross-sectional area. Now you should be able to go a little bit further in this though, because you're told that it's a cylinder. And if you want to look at that cross-sectional area, right, because it's a cylinder, it has some uniform thing. So for example, if it's the cross-sectional area is a circle, that cross-sectional area is going to be given by pi r squared. So you should be able to recognize that the shear force is related to the radius by k times pi times r squared. Or you can go even further and say, oh, but if k is a constant, k times pi is a constant. So this is just going to be the shear force is equal to some c times r squared. So here, if you double the radius, the shear force is going to go up by a factor of 4. Okay. All right, and let's look at a couple more. So in this example, this is basically the way Newton originally posed the second law. The rate of change of momentum is proportional to the net force on the object. So here, what are the two variables? First is the rate of change of momentum, and the second is the net force on the object. So in this case, the momentum is m times v, and the derivative of that is the rate of change of the momentum. The net force, that's just the sum of all forces that are acting on the object. So what does this say? This says that the derivative of mv is related to the net force by taking that net force times some constant. Okay, so this is Newton's second law. What's important about this is that the way that we define units is that if we're using forces being in newtons, mass in kilograms, and velocities meters per second, k equals 1 because of the way we define the units. All right, let's look at one more example. And in this example, say the voltage drop across the resistor is proportional to the current flowing through it. So again, you should be able to recognize what the variables are. First is the voltage drop, and the second is the current. So what's the idea? The idea is we have some resistor. It has some current flowing through it. Okay. And there's some voltage drop as you go across that resistor. So from this statement, you should be able to define that. This is normally defined in units of volts. And then we have some current. We'll call that I. And this is generally measured in units of amps. And so what this means is that V is related to I by this expression where K is some constant, which we don't necessarily know. This is referred to as Ohm's law. And we don't usually call this K. We normally call that constant of proportionality the resistance, right? And this is usually measured in ohms. Okay. So let's look at another thing. So we can say, sometimes you might say A is inversely proportional to B. Okay. If this is the case, we have two things, A and B, and the relationship is that there's some number, we'll call it C, where A is equal to C over B. Okay. So if you're told that two things are inversely proportional to one another, you should be able to find the first variable, the second variable, and recognize that there's some number out there, you don't necessarily know what it is, but that's how those variables are related. So let's look at an example. So in this example, you should be expected to take a statement like this and parse it and figure out what's going on. So we've got some chamber. Don't know what's going on. So this is some Harry Potter nonsense. So you've got this thing going on, and you know that the mass and temperature does not change. If that's the case, you're told that the pressure is inversely proportional to the volume. So from this statement, you should recognize that you have two variables, pressure and the volume. And pressure is inversely proportional to the volume. So there's some number, we'll call it K, where P equals K over V. Right? And what does this mean? This means then that if you double V, you cut P in half. Okay. All right, let's look at another example here, and this is going to be a little different. In this example, the basic physical principle that we're going to use is conservation of mass. So the idea is mass is conserved, which means that if mass enters or leaves, if enters the system, there's going to be a change or a positive change in the mass. If it leaves the system, it's going to be a negative change in the mass. Okay, and that's really all it means. But what's going to make this a little more confusing is we often work in terms of rates that the mass changes. So suppose we have this situation. We have a tank where salt water comes in, right, at some rate and some concentration. So this is rate that it enters, has some concentration, and there's some rate that it leaves. And the question is, we'd like to try to understand how this mass and what's changing in here. And before we decide, we have to figure out what is the basic principle. And so in this case, we're going to say mass is conserved. And the idea is what comes in minus what goes out equals the total change. But what complicates this is that we don't necessarily know how much is coming in. What we know is the rate that stuff comes in, and the rate that stuff goes out, which means that we know the rate of the total change. So what does that mean? That means we have the derivative that stuff comes in minus the derivative, of stuff going out is going to equal the rate of change of what's in this tank. Okay, so this is rate in minus rate out is equal to the rate of change. Okay. So, how do we deal with this? First thing we're going to do is read. We're going to draw a picture. Organize the information. Notice no variables are given to us. We have to define the variables. You have to make that clear. And from this, we're going to have to figure out the relationships between the variables. And we're going to have to do that by applying some basic physical principle, in this case, conservation of mass. Okay, and then after we've done that, we're going to decide how to proceed. And we're going to execute the plan. And notice there's a lot of stuff going on here. If we cannot expect to just simply write stuff down and figure it out. Okay, and here's the other thing is that if I change this for a different situation and you've memorized what to do here, or I change it a small bit, you're going to be completely screwed over. Right? So what's absolutely vital is you know the basic ideas, know the basic principles, and if I give you a slightly different situation, you're expected to be able to react to that and figure out what to do. So let's go back. What do we have? So in this case, read the question. In this particular case, everything's been organized and laid out nicely. This is not going to be the normal case. But what do we have? We have stuff coming in at 50 liters per hour. It has this concentration and how fast it leaves. Okay, so things have been given to us in a very nice way, but that's not always going to be the case. So read it carefully, figure out what's going on. So let's organize the information. So we have, so stuff is going to enter at 50 liters per hour. The concentration is going to be 1/2 kilogram per liter. And it leaves at a rate of 50 liters per hour. Okay, so what's going on here is we have some tank, we have stuff coming in, and what leaves, we're assuming, is well mixed. So we're not going to worry about gradients in the concentration. We're going to try to keep this as simple as possible. So again, it's entering at 50 liters per hour with a concentration of 1/2 kilograms per liter, and it leaves at 50 liters per hour. Okay. Now I'm going to choose my variables, and I'm choosing my variables with the idea that I know that I'm going to try to conserve mass. And this is absolutely vital and important, is that I'm working with mass. Okay, so because of that, I want to focus on the amount of stuff. So this is mass, and I'm going to be working in kilograms because that's the units that are given to me. I'm not working in concentration. This is not kilograms per liters. This is kilograms. Okay, and I'm going to have some volume of the tank, and this is in liters. Okay, so let's explore. The first thing What's happening to the volume? Well, the volume, the rate of change of the volume is the rate that's of the volume in minus the rate out. So I've got 50 liters coming in and 50 liters going out. So the rate of change of the volume is 0, which means the volume is a constant. And since I was I given that? Let's go back. Oops, that was not given to me. Okay, so I got to be careful. This is going to be some V naught. I don't necessarily know what that is, and it wasn't given to me. Okay. All right, so now what else is happening? I've got some rate of change of the mass. So I have A of t is the mass, and the rate that that changes is the rate that stuff comes in minus the rate that stuff goes out. So let's see, what is the rate that stuff comes in? So I got to be careful here. The rate in is going to be in kilograms per hour, and the rate out is going to be kilograms per hour. In terms of what's coming in, let's go back to my picture. What's coming in is 50 liters per minute, 50 liters per hour times a half kilograms per liter. So coming in, I've got 50 liters per hour at 1/2 kilograms per liters, and I need kilograms per hour. Let's see, I've got a 1/2 kilogram there. So I've got 1/2 kilograms per liter. I need to get rid of these liters. So I'm going to do, this is dimensional analysis exactly like what you did in chemistry. So notice if I multiply by 50 liters per hour, what happens? I've got liters on the numerator, liters in the denominator, so those cancel. So I'm left with 50 halves kilograms per hour, or 25 kilograms per hour. And so in terms of what's coming in, that's exactly what I need. In terms of what's going out is, well, see, I've got 50 liters per hour. I don't know how many kilograms are going out, but notice what do I have up here? I have basically concentration times flow rate. So trying to use that idea, notice this is flow rate. If I can multiply by concentration, I'm going to work things out. Even if I don't recognize that. Again, I know what I want, kilograms per hour, right? And I know that there's A of t kilograms in the tank. So now what is this? This gives me, at this point, kilograms, liters per hour, and I'm off by the amount of liters. So what if I divide by the volume of the tank? In this case, whatever V naught is. Okay. If I do that, I've got liters per hour times kilogram times 1/liters. And notice the liters cancel, and I've got kilograms per hour. So for going out, I'm going to have 50 times A divided by the volume of the tank. So this is the rate of change of the mass in the tank. Is going to be the rate in, which is 25, and that's kilograms per hour, minus 50 over V naught, and V naught's some constant, that's the volume, times A, but A's a function of T. Okay. So I now have my differential equation. Okay. Now, I was not given any information about what was there initially. Let's suppose I'm told that there's no salt in the tank initially. And And we might say this is fresh water. So there's no brine or no salt in the tank initially. We might want to know what's going on. If I had something like this, I now have my ODE and my initial condition. Right. So if this was the case, I would have a differential equation that the rate of change of A is 25 minus 50 over the volume times A. And initially, I have 0 kilograms of salt in the tank. Okay. This is going to be a little confusing if I just leave this like this. So let's just pretend the volume of the tank is 500 liters, and that's how much was in the tank initially. If that's the case, right, so I'm going to have 50 over 500. It's going to be 1/10. That's my differential equation, and that's my initial condition. And I'd be expected to solve this. So here's my plan, is I'm going to solve this. And notice I can either use a integrating factor, or I could treat this thing as separable. I'm going to treat it as separable just because that's usually easier. And I'm going to have, when I do that, I'm going to have some constant after I integrate. And I'm going to use this to figure out whatever constant floats out. All right, so let's do it. All right, so I have A prime is 25 minus 1/10 A. I can divide the whole thing over. All right, so I've divided both sides by the whole right-hand side. And now I integrate both sides. And I can treat this, this is basically the chain rule. This is like dA, so I can pretend that it's really this. And now to integrate this, let's see, if I let u equal 25 minus 1/10 A, du is going to be minus 1/10 dA dt, right? So there's my dA dt, but I'm off by a minus 1/10. So let's see, so I had this integral, 1 over 25 minus 1/10 A dA dt is equal to the integral of dt. I had u is 25 minus 1/10 A, du is minus 1/10 dA dt. So that right there is this thing. So that says dA dt is minus 10 du. So my integral becomes 1 over u times minus 10 du equals the integral of dt. This is going to be minus 10 log of u. This can be the integral of, t plus c. So I'm going to get minus 10 log of 25 minus 1/10 A is t plus c. Now again, I have an initial condition, so can I just use this to figure out what c is? I can just do this right now because it's basically already solved for c. So I know that a of 0 is 0. So if I let t equal 0, I get minus 1/10 log 25 minus 1/10 of 0, right? This is a of 0 equals 0 plus c. So c is going to be minus 10 log of 25. So So what do I have? I have now that minus 10 log of 25 minus 1/10 a equals t minus 10 log of 25. And my goal is to solve this for a. So let's do this. Let's divide both sides by minus 10. So I'm going to get minus 1/10 t plus log of 25. Now if I take the exponential of both sides, then e to the log is just going to be this thing. So I'm going to get 25 minus 1/10 a equals minus a to the 1/10 t plus log of 25. Let me simplify this. This is minus e to the minus 1/10 t times e to the log of 25. E to the log of something is just the something. So it's going to be e to the minus 1/10 t times 25. I'm after that. So let's see. Let's subtract 25 from both sides. And then multiply through by minus 10. And now let's just fix this up a bit. Minus 10 times 25 is minus 250 e to the minus 1/10 t plus 250. What's going on here? What does this mean? This means that, let's check my initial condition. When I plug in t equals 0, I get minus 250 e to the 0 plus 250. E to the 0 is 1. Okay, so that checks. As time increases, e to the minus t over 10 is going to go to 0, and my a is going to go to 250 kilograms. Okay. So does that make sense? So notice that after a very long time, my concentrations should get really close to the concentration coming in, which I said was, let's go back to our original thing here, 0.5 kilograms. And we said the volume is going to be 500. So notice if I take 0.5 times 500, I'm going to get about 250 kilograms. So that makes sense. Okay. One last example. No, I'm taking a couple more examples. Tell you what, I'm going to do the next examples in a separate video so we can break this out.